Hello, we are going to see in this video how to add the kinematic model for estimating through dead reckoning the pose of the platform. I will go now to the event loop to add certain line of code you are going to see very soon. One first step will be creating a variable for containing the state of the system. I need to initialize also that variable. I initialize it in this case using the well-known initial pose. That the information pose 0, remember, was provided by the extra information. Now I got to go to the event loop, and at the very beginning of this I will do certain calculation. Before I dispatch according to the type of event, I will run my kinematic model. I will provide the current value of my estimate. I will also provide the value of the dead reckoning sensor according to the last measurement I have, and I also provide the delta t, which is the time that elapsed since the previous event. You may ask, who is maintaining this variable? Okay, this is a vector which is 2 by 1, and that is being refreshed by event of type 2. Here is each time that we have an event that corresponds to a dead reckoning measurement, we process that event just reading the data and generating a copy here in our input vector, which is going to be 2 by 1. In the first component, the longitudinal velocity, and the second component will be the heading rate, which is coming from the gyro. That will be it. Now we want to do some animation. Remember that we had this. Now I could use for showing some capability the API, and here I'm going to specify produced by the kinematic model. I just realized that I had not created that one. I'm going to create that object. So I create the second one here. Put here it is. I had that one. So I call this API function, this helper function, and for showing my original ground truth position. And now I also showing another for the case of the. Alright, we are ready to run the program. I'm going to save and I'm going to run the program. And here it is, it's working. I'm going to pause for a second. We don't realize, but here we do have both, which are going to be very close to each other. And you will see that there are two. Yes, there are two. One blue and the other is red. Red one was the ground truth and the other one was the one which we are estimating through the kinematic model. At the very beginning would be very good, and eventually our kinematic model introduce certain errors, certain discrepancies with the actual system. They start to drift respect to the ground truth. Okay, but we have an issue in this implementation, because if we go here, we have a problem because this dt usually is going to be positive or equal to 0, it will never be negative, except we reset our program. If we decide to reset our program, the time will go to the past, and then we have to have a protection, because if not, we are going to use this kinematic model with negative dt, and we don't want to do that. So I decide to modify this a bit. So each time that the dt is calculated, we are going to ask it dt positive, and then we run this thing. And if it is not positive, it will be 0, or it could be negative. It will be 0 or negative value, which is asking if you are positive. We run this as usually, that will be mostly all the time. But if you are not 0 and you are not positive, I'm going to verify. If you are negative, I will assume that you are resetting. Someone sent you to the past, and then I'm going to reset the state vector which we are estimating here, and set that one to the initial pose, and we are also going to reset the knowledge we have about the input of the system for them to be equal to 0. Bring some message here. Now we run the program, reset. It's going to go to the initial both are together here. We don't see the difference between them for the moment. Now I will do some trick to simulate what happens if I have a small bias in the measurement coming from the gyroscope. I will do that. Go here to event type 2, and remember here we were reading or refreshing this variable, which is the one we are using for feeding our kinematic model. And that is a good practice because these measurements are coming very frequently, about 5 milliseconds or 10 milliseconds. So, but now I'm going to produce or pretend that our gyro is being polluted by a small bias. I decided to put a small bias of 0.1 degrees per second. I'm using anyway radian per second because those are the units I'm using in my kinematic model. So we are going to see very soon that when we have a small bias in affecting our measurement, I'm going to pause the book, reset. I didn't want to do that anyway. So here we have this thing, and we start to see that there is already some discrepancy between the ground truth and our estimate using the kinematic model. Yeah. That is just because we have a small bias affecting our gyro measurement, and the discrepancy will keep growing between the ground truth and our estimate through the kinematic model. So now we are in condition to compare with the ground truth because we have the good luck that's being provided, but in a real application you wouldn't have that advantage. So that is why we need to tune very well, to implement very well all our resources. So this is running well. We go to the program again, and the question is here, which model are you going to use? You have to choose the proper model for this kind of platform and information we have. So we are talking about that our inputs are going to be provided by a speed sensor and by a heading rate sensor gyroscope. This is good. Oh, the rest of all this program is the same that you were doing before, playing in tutorial 2, problem 4, and also maybe trying to implement what we did discuss yesterday in the lecture.